Hello everyone and welcome to another video of myself looking at websites from quantum technology companies. This time we are looking at KIPU Quantum. So we start right away with their website. You can see it here. It says we are KIPU Quantum. And let's see what the company is about and what they're actually doing. So here it says new Qiskit function by KIPU Quantum. eSky Quantum Optimizer, solve complex optimization problems using IBM quantum computers. So looks like here we are again on the, let's say, software level side of things. So this is probably not a hardware manufacturer, because here we see Qiskit, which is an open source quantum computing programming or development language where you can develop algorithms, which is mainly powered by IBM. And that's also what it says here, right? IBM quantum computers. And it is a quantum optimizer, so this is probably useful for optimization problems. But let's look into it. Let's see what it actually says. So it says this function built on the BF-DCQO algorithm is an excellent example for a heuristic for optimization applications, which has the potential to drive us as a community faster to quantum advantage, says Jay Gambetta, Vice President at IBM Quantum. So what does he mean by that? So quantum advantage means basically creating something on a quantum computer that creates a useful solution, or let's say a problem, a solution to an actual problem, right? Like not just an academic thing that somebody came up with, but like using quantum computers to solve problems that are actually being useful for something. And this algorithm apparently seems to be a huge step forward. And we will probably read more about that in a second, but let's see what else we find here on the website. So it says, trusted by the global leaders and experts in the quantum field and leading investors in deep tech. So we see IBM Quantum, probably, as we saw before, they are also offering this algorithm or using this algorithm. Then we see QEra, Pascal, IonQ. So we also have hardware manufacturers here. We see NVIDIA as a big manufacturer for basically AI or GPU hardware. We see, for example, the Deep Tech and Climate Fund. So there is also investors here, or On-Site Ventures, Verve Ventures, QAI Ventures. So there's a lot of venture capital also probably going into this company. And there is to learn more about the company, but we will do that later. We will first look at the rest of this page, because then we go to the next one, which is the About Us one. We have proven that quantum computing is at the brink of beating classical benchmarks for select use cases. Now is the time to move. Want to know if your specific problem can be solved? Yes, get me started. So they're really like on the problem side. They're at the very, let's say, at a very top layer of this whole quantum technology stack. They're looking basically at a way to map probably existing computational problems onto algorithms, and then also work on the algorithms, because before we saw this particular algorithm being advertised. Unlocking the merge of quantum computing with AI at scale will challenge the world. Now is the time to move. Check our solutions for. And now we see actually what the problems they are looking into are. So we see financial modeling, boost neural networks for images. So this is like medical imaging as it looks here, probably something like tumor detection. Then we see classification of tabular data, probably a very broad field where you can actually use that. Combinatorial optimization for logistics, so basically like the traveling salesman problem, I guess. Optimizing networks for telecommunication, chemistry modeling, protein folding. So there's like the typical portfolio of cases that they're also looking into, and probably helping companies to understand how quantum might in the future, or maybe even already, help to create solutions here. Access our software solutions, no physics PhD required. So the target audience is probably people that are working on computational problems, that might have a background in computer science or whatever, and they now want to look into the potential that quantum might offer to those computational problems. It says 200 plus enterprises already signed up to our platform, Planck, with QK at the end. It provides access to our solutions, including cloud-accessible quantum processors, no quantum know-how required. So probably like let's see if it's like a no-code or a low-code type of thing, or if it's like, let's figure it out in the next step. Then there is like latest KIPU news. We see this is from end of May. We are now recording this in June, so this is also, I guess, pretty much up to date. And then, there is also a call to action down here, which says, yes, get me started. Okay. Now let's take a little look at the About Us tab. So who is KIPU? At KIPU Quantum, we believe that quantum computing can have an amazing economic impact and might change our society in many different aspects. So again, it is like at the looking at the economic impact, which is the one side, but it also says here like the society impact plays a role. So they are looking at these two dimensions, and then probably like from the algorithm point of view, from the problem layer point of view, how can existing quantum solutions be used to tackle those problems. Then we see here a nice photo of the whole team. Recreate software that makes quantum useful. We solve real industry problems thanks to our revolutionary algorithms embedded in software solutions. 200 plus enterprises already signed up to our platform Planck. It provides access to our solutions, including cloud-accessible quantum processors, no quantum know-how required. So it says that they are already like industry problems that are already being solved with this, if I understand it correctly. So this is probably already on its way to production. We are the leading team in the industrial quantum solutions. For funding, our founding team brings a previous exit 25 years plus in quantum R&D and unique insights into what industrial quantum users in pharma, chemical, and manufacturing really want. Strong technical leadership team beyond the founders, 30 plus PhDs in the quantum physics, math, computer science, and chemistry. And then it says we have reached a crossroad. Quantum advantage is here. Okay, so they say it's already there. We create co-designed solutions that are powered by our unique quantum physics insights and enhanced by AI. This extracts the best from today's quantum processors. We are 10,000 times shorter than other quantum algorithms, allowing us to beat classical solutions in solution quality for real-world problems. Then we have the founders here, we have the leadership team here, and the shareholders. So these are basically the investment companies. There is also a roadmap here, and I would love to check that one out. So maybe let's quickly take a look at that. KIPU's roadmap towards commercial quantum advantage. The pre-industrial era of quantum computing driven by hardware progress. Mature quantum computing is projected to unlock hundreds of billions in value at stake for large organizations. It is poised to reshape industries alongside the current advancements in artificial intelligence. While Gen AI continues to revolutionize the way we interact with technology, quantum computing is becoming a game-changing reality that's already around the corner. And then, it's about IBM again, and I guess IBM hardware. Then we have here the big mismatch, algorithms are the next bottleneck to overcome. So the first statement was like, okay, we first needed hardware to run something on. Now we have some hardware, which is this NISQ hardware, which we already heard about in other videos here. Now the next bottleneck that they predict is going to be the algorithms. Let's try to understand why. Actually, there is a quite long text here. I'm not sure if I will go through it in this video now, but let's just check the first part of it. However, despite progress on hardware, most of the existing quantum algorithms are still even more greedy for quantum resources than the hardware can provide. This mismatch between algorithms, resource demand, and hardware capabilities prevents us from unlocking the real potential of quantum computing has to offer. With conventional approaches, quantum is more than 10 years away from solving any real problem. So their approach is now to come up with algorithms that can already deal with the intermediate quantum hardware that we have, this NISQ hardware, and which is, let's say, less resource hungry. And resource hungry, what do they mean by that? Well, it means that you need these error-corrected logical qubits, I would assume, and that you need a lot of them. Like in these very initial ideas of how to create quantum algorithms, like the Shor's algorithm, you need really error-corrected perfect qubits that you can run these operations on, like the quantum Fourier transformation. And in order to reach this, it's probably still going to be quite a long time, because we need to have first quite a lot of physical qubits, then we need to combine them into those logical qubits, and only then we can really execute these algorithms. And there is probably some useful stuff that can already happen in between, and this is actually what they are working on, I guess, from how I understand it here. Also, I see here like another very famous algorithm is the Grover's algorithm. We see here 2 billion logical gates. And then, yeah, I guess here it says found that optimizing a portfolio with 1,000 assets would require more than 1,029 gates. We note optimizing 100 assets is also still solvable classically. Okay. So this is now looking at the problem part. Then it says, although IBM's roadmap is forecasting a quantum computer capable of executing the impressive number of 1,109 gates in 2032, the required number of gates is 20 orders of magnitude higher. Okay, so yeah, it basically points out exactly what I said before. Like, you have these early algorithms, but we cannot really expect that the existing quantum systems will deliver on this very soon. And then here it says the birth of a new algorithm paradigm, the death of the old labels. And here it really talks about what I said before. So you see the NISQ, you see the FTQC, so fault-tolerant quantum computing, and the PISQ, perfect intermediate scale quantum computing. So these different paradigms, the stages that we are moving through, going towards these optimized error-corrected qubits. And then we see that here, yeah, probably this is like the roadmap definition. Then we say it says quantifying progress in quantum algorithms with KCI. And I mean, I'm happy to go through this in detail. I just don't want to stretch today's video too long. If you want me to actually go through this, if you want me to talk you through this whole document, or if you also want me to compare this maybe with the other timelines that we've seen from hardware manufacturers and anything like that, let me know down in the comments below. Then I can make a video for this specific topic as well. Let's quickly scroll down here to see this roadmap. The interesting thing is we see 2024, 2025. So we are in 2025 now. So this is like a comparatively short roadmap, but also I think it looks very concrete in what it talks about. So we see here the KCI, KIPU complexity index, which is growing here. We see co-designed algorithm performance, application and use case, services on KIPU's platform, quantum innovations assessment. Okay, so let's look at the application layer. So in 2024, they already said portfolio optimization and image classification were topics they've been working on, as well as job scheduling with mixed integer optimization. Job scheduling is also something that we've heard from D-Wave in a recent presentation or a recent publication they made on their use cases. Then we see for Q1 2025, chem informatics based on graphs. Then we see quantum chemistry simulation based on electronic structure modeling. Then we see for Q3 quantum sampling for quantum machine learning applications, and Q4 protein folding. Protein folding is also a very complex topic where AI is already being employed, I think, by Google too, with also very great results actually. And there is an outlook even here. So looking ahead, the year 2025 holds special significance for KIPU Quantum at the United Nations, as the United Nations has declared it the International Year of Quantum Science and Technology, IYQ. This global incentive celebrates a century of breakthroughs in quantum mechanics, building on the foundation work of pioneers like Werner Heisenberg and Erwin Schrödinger. We also see 2025 as a pivotal moment for quantum technology, emphasizing our confidence that it will be a year full of achievements the quantum industry has never seen before. Okay, let's also quickly take a look at the solutions tab, as time already flies, and I don't want to make the video too long, and we also still have to look at the platforms. So, application and hardware-specific quantum computing solutions. Our solution is based on a revolutionary method. We co-design algorithms that account for problems, requirements, and processor specifications. So we see here the standard algorithm, the application-specific KIPU algorithm, and hardware-specific KIPU algorithm. Okay. So I mean, it doesn't say anything about the problem, but I think it says something about the mechanics, or like the approach that they are doing. So you have standard algorithms that somebody came up, like a theoretical physicist might have come up with, which might even solve a specific problem. And now how I understand it is, okay, this is basically from the world of theory, so you don't make any assumptions about what is even feasible, what quantum computers can do, because up to a couple of years ago, there wasn't even like a very small quantum computing system, right? When I was working in the lab, there were like 2 qubits. So then here it says we use our patented deep physics process to create a short application-specific algorithm for the specific business problem. So this is this DCQC, digitized counter diabatic quantum computing, which is then probably like helping them to reduce the length, the number of gates the quantum processor needs to do, right? It says here maximum length supported by quantum processor. So they basically shrink it down, they chop it off into smaller units. And then the next step is, okay, now this is still like very general, right? So this is like just thinking about it from the gates perspective, right? Just looking at the quantum gates, like how the algorithm is built on this scheme. And then how I understand this one is, now you look at a specific processing architecture, like superconductor qubits and then the IBM platform, or like IonQ, so ion qubits and then the IonQ platform, which all comes with special things that they can do very good and other things that they might not be able to do as well, like coupling multiple qubits together and executing a lot of operations fast, things like this, right? And then here it says we select the most suitable quantum processor and use system-specific blocks to create even more compact hardware-specific algorithms. So this is this digital analog quantum computing, DAQC. Okay, our algorithms beat other quantum and match leading classical approaches for real use cases. Okay, so here we see the KIPU algorithm, next best classical benchmark, and in the alternative quantum method, as in like, I guess the efficiency, right? Okay, so for HUBO, higher order constrained binary optimization problem, solves real-world problems. Okay. So interesting. Then it says something about their technology. So they have this counter-diabatic protocols accelerate solutions of problems in a variety of domains as they allow us to reliably shorten the time required until completion of the computation. We translated to digital devices, these protocols dramatically compress the algorithm, rendering the solution. Okay, and then we see here like the starting point. This is the solution, and then like how the non-diabetic evolution happens. So okay, we see there is like let's say not the solution being achieved, but some unpredictable results. And this is also accelerated, as it says here. Then we see the diabetic evolution, which is very slow, but it reaches the correct solution. And then the counter-diabetic evolution, which apparently very quickly reaches the solution. And then we see the use case, something about the use cases. Performance of our application and hardware-specific algorithms has been validated on existing quantum hardware. 500 times shorter time to solution, 600 times increased success probability, 100 times better results, whatever that means, right? And 1000 times reduced training data for CNNs. CNNs, I guess, is convolutional neural networks. And then again, we see the use cases down here. Okay, let's quickly jump to the platform to also see Planck with Q in it. Easy access to KIPU's QC solutions via Planck, our cloud-based platform. Now let's figure out if it's like a low-code thing or no-code thing or how it works. We see there is marketplace and services, so I guess it's like a dashboard and you can choose the different cases that you want to look into. It says service-based quantum solutions, scalable services, access to diverse quantum and classical hardware. So we see like QPU, HPC, CPU and GPUs. Okay. And then here in this dashboard, like on the home, it says KIPU digitized counter-diabetic quantum optimization, so the DCQO. But then we also have the BFDCQO, which is KIPU's biased field digitized counter-diabetic quantum optimization. Okay, then we see the different hardwares here like QEra, IonQ, IBM, and D-Wave. And then, okay, quantum service store, so that's what it is, right? So you see here again these different algorithms that we talked about before. And I guess you can then use the platform to run those. The power of quantum at your fingertips. Okay, and then, yeah, access to all major quantum backends and simulators. So IBM, QEra, IonQ, D-Wave, Azure Quantum, and Rigetti. And there is probably even more, as it says, explore backends. Yeah, and here is how it works. So kickstart your quantum journey. Looks very much like a Pythonic way of accessing. So here you see program.py. It imports this Planck with Q package, and in there you have probably like all the relevant packages, and then you tell it which backend you want to run this on, and this is probably how you can build applications in Python on this platform. Here it also says increase your quantum readiness. Easily orchestrate services on Planck, for example, to build benchmarking pipelines, to compare different quantum backends, solvers, simulators, or even warm starting approaches to investigate quantum for your use cases. And then here it shows like the pipeline. So you create your use case, you encode it in Python, you generate the quantum circuit. So that's like the different gates, right? And then once you have this gate scheme, there is this function here which helps you to actually deploy it on the specific hardwares. This is also what we saw on the solutions tab before, right, where it showed how the algorithm is being accelerated in this last step. This is what we see here. So this is then optimizing for the specific quantum hardware, and then you can compare the results. You can see what is the best hardware to run your algorithm on. Here it says even more about the features, and you can also integrate it in your existing workflow, as it uses Jupyter, which is like a Python front end, maybe let's call it front end, like a Jupyter notebook. There is Git integration for versioning. You have Python, as discussed before, and then there's also Anaconda, which comes with a whole lot of other packages that you might need for scientific or data science jobs. Okay. And then it says join over 600 users across 200 organizations, and here you can register for Planck. If you want me to register for this platform, then as always, let me know down in the comments below, and make sure to subscribe to this channel so that you don't miss out on me actually going onto the platform and trying it out. And with that, I hope you liked today's video, and I'm looking forward to see you in the next one. As always, make sure to get yourself something to drink and stay hydrated, and see you in the next one. Bye bye.